All right. A good few people have joined already, so I think it's time to get started. So before I begin, just remember during this webinar, uh, please, you can go to the Q&A section and leave any questions, and then when we get to the end, with whatever time we have left, I will answer as many as I can. With that said, I'll turn off the camera and we'll start the presentation. So. Okay, so welcome. Today's topic is on taking measurements in HiPIMS plasmas, basically. So I want to give an introduction to magnetron sputtering in general. Most people who work with impedance are actually from the semiconductor industry, but we do have coding clients, and I kind of want to make sure everyone's familiar with what sputtering is and what HiPIMS is in particular. So I'm going to give an introduction to that, and then I want to introduce, what diagnostics exist for specifically HiPIMS measurements, although what I present today is applicable to all coding tools. And I want to give you some nice data examples and some tour of the software and how you do it if you're using our sensors. So so I want to start off with just an introduction to sputtering processes in general, and then I'll go through some nice data examples and particularly like sub-microsecond measurements of pulsed sputtering regimes with RFEAs, Langmuir probes, and a special Langmuir probe called the Plato probe. I'll also show time average measurements of ion neutral ratios and deposition rates and this sort of thing. Okay, so firstly, let's do a little bit of introduction to sputtering technology. And it's kind of used everywhere. You may not realize that a lot of things around you have at some point touched the plasma. It's a surprising amount of things. A lot of hand tools would have, hard coatings on them that may have been applied by a sputtering tool. Medical implants have protections. If someone has a new hip, it may have been treated by a plasma. Architectural glass and smart glass, vanadium dioxide, I think it is used to coat glass, like a really thin layer. You don't notice it's there, but it will either reflect infrared, when it's too hot, and it will let it through when it's too cold, just purely by the material properties. So there's lots of really neat applications of like these thin films, which are achieved by precision sputtering. So let's talk about the plasma side of things. So here's some pictures for those of you who haven't seen inside of a sputtering tool. So, here's a number of different sputtering targets. So you can think of them as electrodes. They are, in essence, an electrode. But the goal is that you are going to sputter the electrode. You're going to wear it down. So there's a number of different electrode options. Can't remember exactly what these might have different metals, or they might be powered in like a circular motion to help uniformity. And you can see up here a target. And in this case, one of our sensors are attached to the target. Here's what it looks like when it's on. You get this kind of donut ring. I'll explain that a bit more in a moment. I think they call it usually a racetrack. But the idea is that, if you looked at this in really slow motion, you would see like a very powerful ionization dot zooming around. Time average, it looks like this. So this is eroding the metal. So here's like a new target. In use, you start getting this erosion, and then at the end, you go through it, and maybe you go through it a little bit too far. So this is what sputtering is. Just a little note, if you are using a standard plasma chamber that's not sputtering, just CCP, whatever, you're still sputtering, okay? So if you have like an ICP tool and you have a ceramic dome or something, there's actually large electric fields on those coils, and you are sputtering away your ceramic liner over time. It makes it rougher, like you can feel the roughness. And similarly, if you power a bare metal electrode, let's say you have a aluminium electrode or stainless steel electrode or something, you're also sputtering that, believe it or not, and creating particles in your chamber. So just be wary of, if you have a plasma and a bias on a surface that's metal, once the ion energy is above, sort of depends on the metal, but 50 or 100 EV, you're sputtering. But this is intentional sputtering. So this is optimized for it. So if you go to the next slide, give you an idea. So there's some magnetic fields present around here in order to kind of trap electrons and so on. You can sort of see this here, electrons trapped on the B field. You create a plasma. And it's an intense plasma because the electrons are trapped. The plasma is really intensely focused, or should I say confined, right above the target. And then the ions from the plasma are attracted to a negative bias that you apply to the target, and that sputters. Okay, so you can see here the idea of there's this electron motion, and then you have the plasma above, and it's a sputtering process. Of course, sputtering is complicated in itself, but we won't go into the full details of exactly what's happening here. So there are different types of sputtering processes, or sputtering tools, we should say. We have what's called like DC magnetron sputtering, which is basically where you have pure DC being applied, and then you have pulse DC, and then you get into this region where you're applying higher and higher powers, but you're pulsing at different rates, and eventually you reach HiPIMS, which we'll define in a moment. But you can look at this axis here. It's all about the duty cycle. So with DC, you have 100% duty cycle; it's always on, and then the duty cycle sort of limits the power density that you can achieve, right? So in order to make a more and more intense plasma, so if you want to have like faster sputtering rates, so you coat the tool quicker and make a thick layer quicker or whatever, you want to have higher sputtering rates. And then if you're trying to make a particularly hard coating, you want very high ionization rates. So that means you want really high power density locally. But you run into a problem pretty quickly. You have to apply a lot of power to get what you want. And more power means more heat, and more heat means things like this happen. So you can really damage your electrode. So the solution to that is to do pulsing. So you can do really, really high power densities instantaneously, and then have a long off cycle. So on average, your power is low, but at the instant that you're making the plasma, the power is really high. Okay. So here's some schematics of this idea. This is applied power with DC. So you just have constant power all the time. And then, pulse DC. So you see the pulsing. And then as you make the duty cycle smaller, this is when you're approaching HiPIMS. You're on for a very short amount of time. You might only be on for 50 microseconds, 60 microseconds, something like that. And then your off time could be on the order of milliseconds. So your duty cycle is, 1%, less than 1%. So you can apply these really high power densities. So you see over here, the power applied is like hundreds of watts. Here you're reaching a kilowatt. Here you're reaching tens or 100 kilowatts. Well, it's applied for such a short amount of time, you don't get this crazy heating issue. So that's kind of the motivations behind this. So yeah, I think I already went through this, but you want efficient target sputtering, dense plasma, and high degree of ionization, particularly for metallic plasmas, for metallic vapors. If you maximize the ion-neutral ratio of a metallic, when you're applying a metallic coating, you reach the maximum hardness. I should say at this point, I'm not a material scientist, so please excuse some errors here, but I think you get the idea. So what other things can HiPIMS help us out with? So I'm jumping straight into it here. So here's another graph about this this ionization fraction, this flux fraction. And if we do a comparison with DC magnetron sputtering to HiPIMS, you get really, really increased densities. So you can see quite a order of magnitude difference in some scenarios. At the instant of the plasma being there, you can reach 10 to the 19 per cubic meter. That's like similar to like a high density microwave plasma. Like this is really intense. Yeah. You can see here with HiPIMS, you can actually reach really high ionization fractions, like 90% or more. And what this helps with, again, is this material hardness. So this is a comparison of two materials, DC magnetron sputtering and with HiPIMS. And it's all about maximizing this ion flux. And HiPIMS allows us to reach new areas of the structure zone diagram. So you can reach areas like low temperature, high density ions. Yeah, so I think I'll kind of skip past the material science, but you get the idea. With HiPIMS, you can get these densified hard materials, homogeneous, column-free, smooth. smoother results in the end compared to DC magnetron sputtering. There are other methods of getting really high density plasmas, like high ionization fraction. For example, you can use an arc reactor. So you literally just do arc sputtering, but that has its own problems. Like you have, you know, particle creation is one issue. For example, it's a lot more intense there, and you have to also deal with a situation where you might have to deliver 200 amps, 300 amps. And it's much less controlled, obviously, when you have an arc as opposed to this, how can I say, confined racetrack situation. Okay, so in general, I'll give a bit of a texty slide, but HiPIMS discharges are like lower pressure. Pressure depends on the experimental arrangement. And actually, because of the low pressure, because you want a distance between the target and the substrate, and you want to have minimal collisions over that distance, so you run the chamber at lower pressures. Sometimes it can be hard to actually strike the plasma. So there's sometimes these assisted HiPIMS, like hybrid. So there's, for example, microwave assisted or RF assisted or some other. So you basically have a plasma source, and then the HiPIMS applied electrode is nearby. So that's another thing that you can do. But this presentation is not about the HiPIMS technology. It's about the plasma and the diagnostics. So what are the fundamental plasma parameters in HiPIMS? How can we measure them? The on time is only in the tens of microseconds. And how can we measure them spatially and temporally, And again, on this, when you have this really short on times, how can you measure the ion flux, the ion energies, the ion neutral ratios, and so on? So I want to introduce what is possible to measure. You've already seen hints in the previous slides. It is possible to get the plasma density and so on. What do you do? How do you do that? And I want to show you as well, like in our software, is how you actually set that up. So I want to start off in particular with the ion energy and ion flux measurements, because I think these will make the most intuitive sense. So we have a system that's called the Semian PDC, pulsed DC, although we probably should just say it's a Semian time resolved. So the idea is it can give time resolved ion energy and ion flux measurements. It takes a measurement at a single position. So this is like the holder. Then there's a cable that goes to a feed through. This cable can be arbitrary length, although the time resolution actually depends on the cable length, but not significantly. Then you have your vacuum feed through and you have electronics box outside. These can measure up to, when you're applying a pulse to them, 800 eV. When you're applying a pulse, not directly to it, but from across the chamber, it's 2K eV actually. So it's higher than this. You can apply pulse frequencies up to 350 kilohertz. Actually, we're extending that. It can probably go to about 700 kilohertz now. And you can replace the sensing elements. They'll survive about 10 microns of deposition. So after 10 microns, you'd want to swap these sensing elements. So here's a picture of a few of them bundled. But they're easy to swap, just 2 screws, and they pop in and out. So they can tolerate 10 microns of deposition before you'd want to change them. And it is tolerant to, metal deposition and other deposition. We've taken precautions to make sure it survives metal deposition and doesn't have shorting or anything like that. Just a quick reminder of how these sensors work. You have a number of grids. You have a grid that prevents plasma from getting in. You repel electrons, and then you sweep this grid to discriminate ions of different energies. The ion discrimination curves look like this. So the higher the voltage, the lower the current you get until there's no current. And this means at this point you've blocked all the ions. Take a derivative of this, and you see the ion energy distribution function. This is all achieved with voltages applied to these metal grids, these metal mesh grids. And the polarity can be reversed as well. So you can block ions with the like positive ions with the G1, and then with G2 you can do a negative sweep. So if you want to measure electrons or negative ions, that's also possible in this. So anytime I say ions, it could also be a negative particle. I'll show you some pictures of what this looks like installed. So I showed you this one earlier. We can build these systems with mounting screws. So you can mount it straight to a target or put it on an arm. It can tolerate all these things being on. Here's one in a particularly dirty industrial coder, metal coder. This one had like multiple 20 plus kilowatt power sources. I think in this case it was like pulse DC actually. But you can see that this is like a big proper industrial coder, and the wire of the Semian going in and inside. We can also build these for rotational coders, but these would only be for time average measurements if you wanted multiple positions. I should also say, yeah, we can measure at different pressures. So we can go all the way up to about 2.2 torr. So we can go from very high vacuum, like, sub-millitorr, 10 to the minus 6 torr we've measured, whatever. So very, very high vacuum up to about 2.2 torr is the upper limit. It just depends on the internal sensing element. Yeah, so what does the data look like? And I think the best way of doing that is actually by giving you a software tour and show you what the data looks like in the software. And then I'll show you some like nice compiled data from papers. So I'm going to exit out of the presentation and open up the software. So I hope you can see that. This here is the Semian software, Semian PDC software. And over here you can see time resolved. And down here are all the settings I was just mentioning. So you set the resolution, start time, end time, the delay. And down here in the bottom, it'll pick up the synchronization frequency. So you apply TTL, you'll see that here. And then this is the graph. So you'll have the ion energy and the current. So sorry, the blue is the ion energy distribution function, and the red is the voltage current graph. And down here you can see there's a time in nanoseconds, right? So this was taken with 5 microsecond resolution. It was a 2 kilohertz pulse, and I can just scroll through the data. So you can actually see the plasma coming on. So you see the ion energy is increasing, the ion flux is increasing. So it comes on, strikes, stabilizes for a while. So this is now we're in a stable plasma condition. And then at some point, the pulse should turn off. This was like pulse DC. It was a 50% duty cycle. There we go. So at this point now, the applied voltage is off, and you see the data dropping down and down and down and down. So this is measuring the afterglow. So the plasma potential is collapsing, the plasma itself is collapsing, and the ion flux is reducing. Okay. Now in this case, I think that we don't fully reach like at 2 kilohertz, the plasma doesn't fully extinguish. So you can see all the way to the end, there's a little bit of still a little bit of flux at near zero. So that you can see the plasma potential is really collapsed. If I go backwards, you can see that when the plasma is on, this was in a grounded situation, plasma potential is about 26 volts. So you see on the energy here. So again, plasma igniting, plasma stable, and this is all in the 5 microsecond time scale, and then plasma extinguishing and afterglow all the way to the end. So this is what the data looks like when you collect it in the software. When you're about to take the scan, when you've set up all the settings, it will tell you down here how long it will estimate the scan will take. So this system requires, multiple pulses, and it keeps setting different delays and then takes measurements. So this will take many, like, this could take 30 seconds or whatever to build up all of this sub-microsecond data. It will tell you exactly how long depending on your settings. And if it's too long, you can reduce the averaging or reduce delays or so on. But yeah, so then you can take this data out and plot it differently. So everything is exportable to CSV. And now we'll go back to the presentation. Go back to full screen. And I'll show you some results in papers from this. Whoops, laser pointer. Okay. Hopefully this is still visible. So this is one example. So there's in this case, the plasma was pulsed up here, and down here was the RFEA. It was grounded again. Yeah, there was an extraction grid as well. So the top electrode was pulsed. There was an extraction grid here with some voltage applied to it. And then there was the sample table. And in this case, the time is coming towards you. So you can again see this plasma ignition, stabilization, and then afterglow, and the plasma collapse when the bias is off. The reason why the ion energy maintains at 100 here is because there's an extraction voltage here. So that's keeping some ion energy all the time. Yeah. So this is what it looks like plotted in a nice 3D graph. And then in this case, the polarity was swapped as well to measure negative ions. So same idea. And what you could see is like this here is the electron energy distribution function. And this is the collapse of negative ions. Okay. The reason why energy is negative on the axis, it's just to do with how you plot it. Like the sign is actually the polarity. Okay, so this is electrons and negative ions. Yeah. I'll give you some more examples. Like here's just the same sort of data plotted. You can monitor how everything lines up with the pulse. So actually, I'll just go to the next example. This is an example from University of Illinois in partnership with Starfire. So Starfire make HiPIMS and pulse DC power supplies. And in this case, it has a kick. So with HiPIMS, you don't just necessarily fully apply a large negative bias in order to attract in ions. In the moment after that, you can charge a positive you can apply a positive voltage for a short amount of time to then kick away all the ionized particles that you care about. Because sometimes what happens is you get this trapping, basically, like you create these ions, they're sputtered, but they're attracted back towards the target with the negative ions, the negative potential on it, sorry, with negative potential. So by then quickly switching to a positive kick, you can then kick the ions down, and this is the same idea, these time resolved results, main pulse, and then the kick. And this kick also helps control the ion energy. So if you do like plus 200 kick, it's going to give you plus 200 ions, plus plasma potential or whatever. And here it is in different scenarios. So this is a really nice paper. I recommend reading it by Jekyll 2023. And then there's other ways of applying this data. This is comparing different scenarios here with HiPIMS and with HiPIMS on and off, and looking at the ion energy distribution versus time and looking at the different energies. So this graph's a little bit harder to sight read, but I think you get the idea. You can really study the temporal evolution of the energy influx basically in different scenarios, even down to these sub-microsecond levels. I'll skip ahead a little bit because we have too many slides. Here's another example of this is a DC sputtering, pulse DC. But you can see the different on times, off times, and the sort of data you can get. Okay. And this has been used to study different metals under different conditions. Like this is a multi-cathode situation. Yeah. So the next thing is okay. So you can measure the distribution versus time and the flux versus time. What about the deposition rates and the ion neutral ratios? They're another important factor, especially for HiPIMS. If your goal is to maximize the ionization fraction, you have to optimize that. How many microseconds do I want to have the plasma on? How long do I want to have to kick on? These are the things you have to optimize. Do you want it on for 25, 30, 35 microseconds, which will give you the maximum ionization fraction without secondary effects causing an issue. So, so we have this system called the quantum, which measures ion energy and ion flux. It measures time averaged. It doesn't measure time resolved, just so you know, in this case. So it can take a measurement like once a second, let's say, for ion energies and ion flux. But it additionally has a embedded quartz crystal microbalance underneath the grids. So these are the grids I showed you earlier on, the G0, G1, G2, G3, and then there's a quartz crystal microbalance, which is also a collector plate. So you can measure ion energy, ion flux, and then measure the deposition rates. But you have the ability of blocking ions and blocking electrons. So you can purely look at the neutrals or radicals if you're looking at etching. But if you're looking at deposition, you can purely look at neutrals and separate out what the ions are doing versus what the neutrals are doing and get the ion neutral ratio measurement. So just for the specs really quickly, it's a 4-grid RFEA. It can actually go to 2 kV now. We've extended the range, so it's a 2 kV ion energy range. And you can apply up to 900 volts peak-to-peak RF bias directly to it. Although in deposition, that's not normally done. But if you're doing biasing, it's safe to apply biases directly to the sensor. And the same idea, easily replaceable buttons. At the moment, the release product is up to 300 millitorr, but we've, as early as yesterday, as recently as yesterday, I was actually testing a quantum system up to also 1.5 torr. So these do also operate well at high pressures. And the idea is, you can see we're only measuring at one point, but there's 2 sensing elements. One is a measurement and one is a calibration, where internally it's actually blocked, so no ions get in, and this is a temperature reference. So this means if you don't have cooling available, like if you have this mounted on an arm or something, you'll still get the correct deposition rate without correcting for temperature. And this can also operate within an RF bias. So if you just get an off-the-shelf quartz crystal and you try to operate it with RF in the chamber, you have a lot of trouble. We've solved all that RF side of things. It's shielded. We have electronics that can pull out the signal. So this works well with in RF environments. And as I said, it can measure the ion neutral deposition rates directly and get the ion neutral ratio. So here's some screenshots from the software, but I'll jump into it in a second. So you get the I energy distribution again, same idea, and then you go to the deposition mode and you can look at the different rates. So I'll jump into the software and show you. Is this one? Yeah. So the idea is you like these don't have the default values actually, but you would measure the ion energy distribution function, and let's say your highest energy ion is 30 EV because it's just a plasma potential. So you'd put in here something like 60 volts to block all those ions. You would have a secondary electron repeller, which would be, I don't know, some negative value with respect to this. It doesn't matter what it is really. And you can set the collector voltage and G1 voltage, your electron repeller. So this is usually minus 80 or something like that. So this blocks the electrons, this blocks the ions, and then you have a switch time. And what the switch time is, either all these grids are like 0 and letting everything in, or they have these potentials applied, and it will switch back and forth, over this time frame. So in this case, it was 100 seconds. So I'll talk you through the graph. So on this axis, there's frequency. Okay, so this is the quartz crystal frequency. It's a standard, Infocon 6 megahertz crystal that's built in. And as you deposit, the crystal frequency goes down. So this is this general slope here. And then when it's blue, that's when neutrals and ions are allowed in. So all these are set to 0. And then when it's red, only neutrals are allowed in. All the ions and electrons are blocked. And then that means you can every cycle, every switch cycle, the slopes are measured, and that will populate these. So you get the neutral only deposition rate, the neutral plus ion deposition rate. Then it will switch, extract from that the ions only, and in this case, it's depositing. If you have higher energy ions, they etch, and this will you'll see a negative value here, and it'll say etching here. And then it will give you the ion neutral ratio based on this data. So you can measure this directly. And this is being done then for optimization of how you power sources. Okay. This is a pulse DC data set, but this has been used in all sorts of systems. So at this point, I'll go back to the papers. I'll mention offhand, like we can measure deposition rates and etch rates. But that's a topic for another day. So if we go back here. Okay. I've shown this before in other presentations, but with the ability to measure the ion energy distribution function, the ion flux, and the ion neutral ratio, that's really, really helpful for doing process transfer. Okay. So the idea is if you're going from like a small tool to a very large industrial tool, you want to make sure that the ion neutral ratios are the same in order to get the same material properties in the end. Okay. So this is critical for process transfer. Like if you have an R&D tool and you want to industrialize it, you need to know the fundamental plasma properties and the fundamental, plasma surface interaction numbers. Like if you just try to copy the pressure, the power you applied, and all this sort of stuff, it doesn't make any sense. And if you try to just do linear scaling, like, okay, my chamber is 5 times the volume, so I apply 5 times the power, not so straightforward. You want to know what your energies were, the flux was, and the ion neutral ratio was, and then you can much more easily transfer processes very rapidly from tool to tool. Okay, and this Ralph Bandor from the Fraunhofer Institute did some really nice work on this maybe 10 years ago and published some data. I can show you this. This is from Bern, where they have is this from Bern? Yeah. So this is from Bern, where they have they have a HiPIMS system where they also have a microwave VCR source nearby. So it's basically a microwave assisted HiPIMS situation. So I mentioned earlier, sometimes it's beneficial to have a plasma constantly there that the HiPIMS system is sort of, how do I say, extracting from, working with. Um, so you can control the plasma with the microwave source, and then you have the HiPIMS sputtering happening. And we can have a look at the different data. So you can have a look here where the deposition rate was measured. And you look at, this case is changing flow rates. You can look at the ionization fraction. So this can all be directly measured using the sensor. Let me go to the next example. Yeah, here's another example. So 3 different targets, silver, zirconium, and copper. Where by playing with the pulse width, so going from 25 microseconds, 50 microseconds up to 100 microseconds, and using the quantum to measure the ionization fraction. So for example, for copper, you can see that 50 microseconds actually gave the highest ionization fraction compared to 25 or 100 microseconds. So this was a way of optimizing the flux fraction, the ionization fraction. So this is with a quantum measurement. Whereas in the case of zirconium, it was actually better to have a shorter runtime to have the maximum ionization fraction. Yeah, so you can use this for optimizing the pulsing parameters for the HiPIMS source. Yeah, so this is all done with the in situ quantum system. We can also study this with Langmuir probes. So Langmuir probes measure the plasma density, so the electron density, ion density, the plasma potential, the electron temperature, and these sort of things. And these are also they're time resolved. So normally a Langmuir probe you can stick directly in the system. We have these solid shaft Langmuir probes, but we also have these flexible probes with holders at the end, and there's a Langmuir tip in the middle. And these can have mounting screws. So this is really handy for mounting inside of coders at awkward angles or putting on an arm to measure spatially. But you can also measure temporally. So our standard Langmuir probe has an 80 megahertz sampling rate. So you can go down to like tens of nanoseconds time resolution. Now, if you have RF present, we have to include filters, and that slows it down a little bit, but you can still get like around 1 microsecond resolution in that scenario. We also have a deposition tolerant Langmuir probe, which even if you're sputtering like oxides or something that's non-conducting, because a Langmuir probe requires on the tips being relies on the tips being conducting. If you have a non-conducting material, we have a probe which can still measure the ion density and electron temperature, even when it's deposited on, with up to like between 10 and 50 microns of deposition, still get accurate measurements. So just be aware that we do have deposition tolerant probes as well as the standard probe. The deposition tolerant Plato probe also has a 1 microsecond resolution available. I can go through the specs, but in general, we can measure a very wide range of plasma densities. It's actually wider than this. It just depends on what tip area you have pretty much, and the electronics. Very wide current ranges. For the deposition tolerant probe, it's like plus or minus 30 volt scan range. But with the Langmuir probe, it's plus or minus 150 EV. We can also provide linear drives for moving across a tool. Okay, so here's some data examples. I'll actually go to the software again just to show you in reality. So if I open the Plato software, this is the Plato software here. It's quite simple. You go to the settings and you input what your pressure is, your temperature is, your collision ratios, and the probe area. And then you go to configuration, and you either have a time averaged or a time resolved. And in time resolved, you set the sync frequency. This is also picked up by the sensor. The resolution start, time, and end. And then it will give you a time resolved result. And you get, IV curves like this. And so this is again with the deposition tolerant probe, and you get the electron temperature and the ion density. No, I didn't have time resolved data available for this webinar, but I have like versus position. So it's the same idea. You have a slider and you can look at the results versus position. You can also export this and make some nice plots, which I'll show in a moment. Yeah, so instead of position step, it'll be time step, and you can view the trends. So this is very easy to use. If I go to the Langmuir software, so here I actually have some time resolved data. This plasma wasn't pulsing. I just had time resolved on, and this was a 10 microsecond step. And you can see the curve here. It is actually updating as I move. It's like wiggling a little bit. You can see the parameters change a small bit. But yeah, you can get very small time resolution. And it's the same idea here. So in the settings, you set your temperature, your pressure, the holder, the measurement tip dimensions, and then you go to the configure, and you go to time resolved. And same idea, set your time, set this. There's a TTL signal you give to the box. So again, in the bottom corner, it'll give you the sync frequency. And down here, it will calculate how long it will take to do all these measurements, depending on how much averaging you're doing and how small the step. So this will say it's going to take 30 seconds to do all the measurements, or 10 seconds, or whatever. Yep. So this can be used for time resolved results too. So I'll show you some nice examples from papers now. With a Langmuir probe, like the standard Langmuir probe, you get a lot more parameters. So this is the plasma potential, floating potential, electron temperature, which is like critical for modeling, electron density, ion density, and you also get you can also get the EEDF as well. Okay, let's go back to the presentation. So I just wanted to show you the software to show like how easy it is, because there's no complication to set up this the pulsing scenarios. So let's just skip ahead a little bit. So this is back to the burn source again, that chamber. And these are some really nice results from Caroline Hain. So here is plasma potential, electron temperature, ion density, and electron density with HiPIMS, and then with this microwave assisted HiPIMS. So a microwave source was used to keep a plasma going. You can see that here. So you can see that the plasma is on. The green section is when HiPIMS is on, and then there's kind of the plasma going back to where it's settled. So you can see what the electron temperature is versus time, and the density is versus time. So you can look at this evolution. And what HiPIMS, it has quite different behavior compared to with the microwave present. But you can see that you can measure, like you can see an interesting effect here, right? So the Langmuir probe is some distance from the source, and you can see that the HiPIMS is here, but there's a lag because the particles have to travel across the chamber, right? So like ionization has to happen and then it has to travel. So this is when the pulse is applied, but actually when we take the measurement, then it's a bit delayed. So that's interesting. But there may be more to that. I think read the paper to get the full details. Yeah. Okay, and then this was the source voltage and current for reference, and it was a 30 microsecond on time. So this 30 microsecond on time on the source produced these plasma parameters on the way. And here's just some other examples of like electron density and other parameters with HiPIMS on and off. And the afterglow, you can see here the plasma potential collapsing, and then the strike settling. So you can see how quickly actually you have a plasma forming. Like in this case, if you used only a 5 microsecond on time on your HiPIMS source, your plasma wouldn't have even formed and settled by then. Whereas here, by 50 microseconds, it's pretty much settled. So this is why you can learn quite quickly using these sensors. Here's like EEDF in time resolve situations. Yeah, just to show the deposition tolerant probe, the Plato probe. This was used in an industrial coder, placed at different locations near these turntables, and measuring on a like microsecond time scale what the ion density was as these coders rotated, and the electron temperatures and so on. Yeah, these are in sputtering conditions. Like I have myself used the planar Langmuir probe, this Plato, in these magnetron sputtering systems, and like afterwards when taking the probe out, you could really see like a thick layer deposition. I didn't put it in the slides, but I have a photo of like using a knife to scrape off, from the tip. The tips are replaceable, but I didn't have a second one. So, even with really thick thick insulated deposition on the probe, we could still get these plasma parameter measurements, electron temperature and ion density. So that's everything I wanted to show. So we went through conventional sputtering processes and why people like HiPIMS. HiPIMS is a very deep topic and huge conference sessions on these things. So barely scratched the surface, but I think you get the idea. And with a Langmuir probe and RFEAs, they're available to do measurements in these systems. And we can also do these ion energy, ion flux, ion neutrals. So um, that is everything. And at this point, I will, I guess I'll answer any questions. I'll go through the Q&A. So feel free to add to the Q&A. Let's take a look. What is the typical current during DC biasing of the plasma? We normally had milliampere readings, so now too high, apply 100 volts. Any region that could cause two conductive plasma? Question is related to P, uh, plasma CVD processes. Not seeing the presentation. Okay, that was fixed. So, but thanks for pointing out. What's a typical current during DC biasing of plasma? Well, this depends on it would depend on the plasma density, right? So, that's normally had milliampere readings, but now it was too high and unstable to apply DC bias at 100 volts. Yeah. So, two conductive plasma. No, okay. There's a lot that I can say regarding this question. One thing you have to keep in mind, so if you have a plasma that's powered by, like, say, pure DC, so DC magnetron sputtering or whatever, you have to keep an eye on what kind of current you're providing to the plasma, right? So we've actually seen situations where people were trying to measure a plasma where they had, like, their DC power supply had like 100 milliamps, let's say. And then they had a Langmuir probe in and they were trying to collect Langmuir probe data, but the Langmuir probe data didn't make sense. It was curving back on itself. It looked really strange. But if you look at the amount of current the Langmuir probe was drawing, it was approaching the current that was going into the plasma. So you're completely, sucking out all the ions. So you just keep that in mind. So there is a dependency. So you have, I'll give one hint here. Think about the power for this situation. So you have 100 volts applied as a bias, and you have some current. So if you multiply those two, you have a power. Okay. And how does this ion power compare to the power that you're delivering to the plasma? If that makes any sense. So with the very limited information here, that's probably all I can say. But yeah, so you have to consider, like, the DC current will depend on the plasma density. If you have to think about how much power is being drawn out by the DC bias multiplied by the current, and how does that compare to the power into the plasma? Yeah, too conductive a plasma. I'm not sure about that. You have to keep in mind actually the walls of a plasma. So if you use, like, very coated, like if you have anodized walls or coated with some insulating material, you have to be aware that charge balance, like, you have to treat the plasma more like a capacitor in that state than a conductor, because there's, you're not closing circuit with ground. It's probably making absolutely no sense. But feel free to email me and we can go through more details, Raj. Anonymous, is it possible to prepare crystalline materials using HiPIMS? Absolutely, yes. Yes, it is. Now, this is more of a material science question, but you can, by maximizing the ion neutral, it might actually go, okay. So by maximizing this ion neutral flux, it actually helps with the crystallinity. Like, that's why you get this much harder materials. There's a really nice paper on this topic by the US Naval Research Laboratory. So, Anonymous, if you send me an email, I will send you a really nice paper, which is all about exactly how you go from amorphous to crystalline in these depositing scenarios. So there's a really, really nice paper on, like, that really details this with the fundamentals. Jose, thanks for the webinar. No problem. Vladimir, how do you trigger the measurement? There's the electronics box. I don't have a picture of the back of the electronics box, but the electronics box has a BNC labeled sync or TTL. So you input a TTL and that does the synchronization, and you can set delays in the software. But that's it. The trigger to start measurement, you just press start scan. with the RFEAs, it's manual. With the Langmuir probe, there is an additional trigger port, which allows you to start a scan with an analog signal. So you can send a voltage spike and it will do a scan at that exact moment. So the scan kind of preps and then it's ready to go. So the Langmuir probe has a slightly different way of doing that. I hope that answers your question. So yeah. For ion neutral ratio measurements, is there a method for excluding the argon ions? Are you asking well, yeah, yes. So you can exclude any ions, but you can't discriminate what ions you exclude. You either like it's all based on the energy. It's like it's not mass dependent. So if you have, as long so the sensors that I've shown you today, like these ones over here, right? The ones that you can mount. So you can actually mount them on the source, sorry, the substrate area that you're sputtering to, or the target. You can actually mount it directly on the sputtering target if you want as well. And as long as you measure what the ion energy distribution function is and know what your highest energy ion is, you can you can set a high enough G2 blocking voltage in order to block all ions, but it will always block all ions. It won't discriminate by particular particles. But yeah, in general, you can block those. Kindly share this paper. Will do. Can you please explain more how to measure the ion to neutral ratio? Sure thing. So I'll just move this over here and I'll go back. So the way that we measure the ion neutral ratio is as follows. We have a quartz crystal microbalance, and the quartz crystal microbalance can measure deposition rates. So we're measuring the ion neutral ratio based on the deposition rate of the ions versus the deposition rate of the neutrals. No, okay, ions can also be etching, but that's the idea. So either all of these metal grids, if they have 0 volts, then all ions and all electrons and all neutrals will enter and we measure a deposition rate. So let's say we do that for 10 seconds. And then for the next 10 seconds, we block all electrons with this second grid and we block all ions with this third grid here. And then you're measuring neutrals only. So this gives you the ratio of basically the ion neutral surface interaction, if that makes sense. That's what this is doing here. And you'd see that in this data here. So you see the neutral number and the ion number, and it's just neutral number, neutral plus ions, you subtract the two, take the difference, and then you get the ratio, which is just a division, if that makes sense. I hope that explains it. There are indirect ways you can do this. So let's say you didn't have a quantum, you only had a semion. What you could do is you just measure what the ion flux is, which is given in the software. Like it's basically we measure the current here, and we know this area, and we know this transmission. So we know what the flux is up here. If you know what the ion flux is, and then you know what your pressure is, your neutral pressure, from the neutral pressure, you can work out what the neutral flux is, right? That's, you can use ideal gas laws or whatever. And then you have the ion flux measured, and that will also give you what the local ion neutral ratio is. Okay, so that's an alternative method. Similarly, with the Langmuir probe, you can measure the plasma density in a certain location, and then with your pressure and ideal gas law, you can work out what the neutrals are, and then you have ionization fraction at that point. That's how you do that with all the different sensors. Are there any more questions? We haven't had any more submitted. So if there are no more questions, I will end it here. So, maybe one more came in. You mentioned the ion neutral ratio versus charge voltage. Can you explain a bit more? Thank you. Versus charged voltage. Do you mean the voltage applied here, or do you mean the voltage on the source? Voltage on the source is basically, well, more power on the source. More power delivered to the plasma, more flux, like more ionization. Is that what you mean? Otherwise, do you mean like I'm not entirely sure. Like another way of actually increasing ion neutral ratio is by applying a bias to your substrate. So you draw in more ions on purpose. So that will change the local ion neutral ratio. I didn't add it to this presentation, but there is a paper published on that. Yeah, it was a paper published 2021 where they were looking at ion neutral ratio of chromium, and they applied different biases like, -10, -20, -30, -40 DC bias in order to increase the ion neutral ratio at the substrate. So then they could study different chromium layers depending on the flux fraction. Okay, you mentioned ion neutral ratio. What's the role for neutral? What is the role for the neutral argon considered? Like if you have just so ion neutral ratio is more important for the metals. Okay, I think I understand your question here. So for ion neutral ratio, what matters more is, let's say if you're doing metal sputtering, the ratio between like, sputtered tungsten, which is not like when you sputter something, it doesn't have to be charged, it may be neutral. So let's say you're sputtering titanium. So you have like, actually it's similar to put in here. Like here when they're sputtering copper, for example, what's the ratio of copper sputtered, like neutral copper versus charged copper, and that's what matters. Now, yeah, so like say if you have an argon plasma, that may interfere. Now, what helps with that is if you you have the source pretty far away from the substrate, that will help like keep because the plasma is really confined, so the argon is confined, and it should only be the sputtered metals that make it. So that's one way of filtering the argon out a little bit. Argon does have an impact. So again, I'm not a material scientist, but I know that if you have argon, so let's say you're depositing layer by layer by layer, if you have argon being trapped in there, that can like form bubbles, basically, or that they can like migrate through that layer and cause voids to happen and this sort of thing. So you want to minimize the amount of contamination by your plasma. Like yeah, like there's some people who try to do like, you know, strike a plasma with a metal instead of even using argon, or only having argon on for a short amount of time, like pulsing the argon. So instead of so you can um there's people who pulse temporarily. There's actually people who pulse spatially. So there's some check groups that do spatial pulsing, and then you can also pulse the gas. So you could have the argon just on for a moment and then turn it off to help minimize this effect. Speaking of money, how much will it cost to implant the devices? I'm afraid you have to ask for a quote. But send me an email and we can let you know. Okay, these neutrals just refer to the depositing ones, correct? Yes, 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 and yes. So that it's only what's deposited. That's what we think is most important. The ratio of the deposited neutrals versus deposited ions. Yeah, yeah. That makes sense. Do you have any data validating repeatability of these sensors, assuming using a stable, mature process and hardware? What's the variability of one sensor per 21s, variability sensor to sensor? Very good questions. So we calibrate the electronics box and the feed through that come with these systems. So like, for example, for the voltage sweeps, we use like a 0.1 volt power supply, and they're calibrated over the range. So that they're pretty good actually. That they should be correct within about 1 volt. And we calibrate the current as well, and that's correct within something like less. We only ship it if it's less than 10 nanoamps or something like that, offset. So we calibrate those two. So in terms of the ion energy measurements, they're completely repeatable. So if you go from sensor 1 to sensor 2, doesn't matter. The ion energy is always repeatable. Ion flux is different. Ion flux depends on the transmission of those grids. So if we go back a little bit, we look at this here. So the transmission matters for ion flux because we're measuring current down here, but that has to pass through these grids. And if you're depositing, you are coding this up. So in reality, when you're using these sensors, you have to have a reference process that, so you would run a reference process, and then if you're depositing, after a certain amount of time, rerun the reference process and see how much your flux has dropped, which in other words is telling you how much clogged this is. Okay. Now, when it comes to ion neutral ratio, it doesn't really matter anymore. So if the sensor becomes more clogged up, the ratio is still the same for what's deposited. So that's fine. So it's only the ion flux that you have to worry about for sensor to sensor repeatability. in terms of the repeatability of ion neutral measurements, we use a standard 6 megahertz Infocon quartz crystal, so it's as repeatable and reliable as they are, I guess. Yeah, but it's only the absolute value of the ion flux that will be different sensor to sensor. It like that number is probably 10-20% sensor to sensor if we do a theoretical calibration. There are published methods of doing relative calibrations to get them within 2%. If you want, if you send me an email, I can send you that paper. It's from Bochum University. But yeah, so ion energy should be perfect all the time. Ion flux will vary with sensors and with the vary a little bit with sensors, and it will vary with deposition. So you have to have your own local reference to make that correct. And ion neutral should be fine. I'm sorry that that's just words, but I think this makes sense, right? And there's papers published with this measuring this variability. So yeah, email me and I can send you those papers. We have 2 minutes left. Any other questions? I'll give it a few seconds. Okay. May I get your email? Yes. Well, did I don't even think I put in my email address in this presentation. Well, if you email info@impedans.com or support@impedans.com, the email will come to me. I will get it. You can also email thomas.gilmore@impedans.com will reach me too. Yeah, so I think we will leave it there for today. We're just out of time. Thanks very much, everyone, for attending. And yeah, email me with questions. We will send this the recording and the presentation out shortly. And any questions and emails in here, please give me a few days to get back to you. But I will reply to you. All right. Thanks, everybody. Bye-bye.